In the previous lecture, we defined a general expression for the change of a quantity over a specific time interval. We will now apply it to the change of position, which is also called displacement. The change of position is evaluated by subtracting the position of the object at the beginning of the time interval from the position of the object at the end of the time interval. Displacement is also a vectorial quantity. We can rewrite this equation slightly differently. In this format, we can see that the displacement is what needs to be added to the initial position to get the final position. Let us show it graphically in 2 dimensions. This curve is an example of the trajectory of an object restricted to travel on the plane of this page. We will place the origin here and choose a location for the starting point for the time interval and draw the initial position as the red arrow. Similarly, this blue arrow shows the final position vector. The green arrow is the vector that needs to be added to the initial position for the sum to be equal to the final position. The green arrow is the displacement. Notice that the green arrow has its tail at the location of the object at the beginning of the time interval and its tip at the location of the object at the end of the time interval. It points from where it had been to where it will be. Since both locations are on the plane, the displacement vector will be parallel to the plane. Choosing 2 different points on the trajectory would lead to a different displacement. The displacement is very dependent on the time interval chosen for its evaluation. Let us look again at the example of the motion along a straight road between Toronto and Montreal, which are 600 kilometers apart, with Kingston halfway between the 2 cities. We will choose the origin at the location of Toronto and the x-reference direction as pointing from Toronto towards Montreal. As an example, a trip between Toronto and Montreal has the following component of position versus time graph. The interpretation of this function is that the car left Toronto at t=0, arrived at Kingston 3 hours later, stayed in Kingston for the next 3 hours, and continued towards Montreal, which is reached 9 hours after leaving Toronto. Let us evaluate the component of the displacement for the time interval from 0 to 3 hours. For this time interval, the final component of position is 300 kilometers, and the initial component of position was 0 kilometers. So the component of displacement is 300 kilometers. The displacement on that time interval must be expressed by multiplying the component of the displacement with the unit vector x hat. Let us now repeat this calculation for a different time interval, the time interval from 3 hours to 6 hours. For this new time interval, both the initial and the final components of position are 300 kilometers, which makes the component of displacement 0. The vector displacement is also 0. This should not be surprising since the car stayed in Kingston during the whole time interval. The total displacement, which we will label delta D capital T, is the sum of displacements evaluated over successive time intervals. Successive time intervals are such that the ending time of the first one is the beginning time of the second time interval. For example, let us call delta D1 the displacement from time t0 to t1, and the second displacement is over the time interval t1 to t2. The time intervals are successive. The total displacement is the sum of these 2 displacements. If you replace the displacement with the relation they have with the positions at the beginning and at the end of the time intervals, you get this. The position at time t1 can be cancelled, and we are left with this, which is the displacement over the time interval t0 to t2. To illustrate the previous setup, let us use this example of a trajectory in 2 dimensions. We will pick 2 points on the trajectory to create a displacement vector delta d1. The tail of the red vector is where the object is at t0, and its tip is where the object is at t1. We will pick a 3rd point on the trajectory for where the object will be at t2, and draw the vector delta d2 in blue. Adding the red and the blue vectors gives the total displacement, which is the green vector. You can see that it is the displacement over the time interval from t0 to t2. It is now time for a numerical problem illustrating how to evaluate the total displacement. Peter is having a walk in 2 segments. First, a 2.5 kilometer walk towards the north, followed by a 2 kilometer jog towards the northeast. We want to evaluate the total displacement for the whole trip. We will use the usual reference directions of east and north. The first displacement is towards the north, and we will label it delta d1. The second displacement, labeled delta d2, is towards the northeast, which means that the angle of deviation from the north is 45 degrees towards the east side of north. The total displacement is the sum of delta d1 and delta d2. We will label the sum as delta d capital T. We could solve this particular problem by working with the triangle that these 3 vectors are forming, using the sine law and the cosine law. After all, we know 2 side lengths and 1 angle. But I prefer working with components, and the fact that we would be working with right-angled triangles only. We will break delta d2 into 2 vectors to form a right-angled triangle with shorter side lengths proportional to delta d2x and delta d2y. Notice that the orange vectors are both in the same direction as their reference directions, so the components of delta d2 will be both positive. We will define theta as the angle of deviation of delta d2 in respect to the north direction. Since the final answer needs to be given in terms of magnitude and direction, we will also define the angle alpha as the angle of deviation of the total displacement towards the east of north. The list of givens is the following. We use the trigonometric ratio for cos theta, and after substituting the givens, we get the value for the y component of delta d2. Similarly, the sine theta is used to get the x component of delta d2. We are now able to evaluate the components of the total displacement. The x component of the total displacement is the sum of the x components of the 2 displacements. Similarly, the y component of the total displacement is evaluated this way. We are not done yet with this problem. We would be nearly finished if the question had been to give the displacement for the whole trip. Giving your answer in component form would have been enough, but here the answer needs to be given in terms of magnitude and direction. Let us start by evaluating the angle alpha. We will use the trigonometric ratio tangent alpha. Isolating for alpha gives this, and substituting the values for the component of the total displacement from the previous page gives this. Using a calculator leads to a value of 20 degrees. We can use the Pythagorean theorem to find the magnitude of the total displacement. Substituting the numerical values for the component of the total displacement gives a magnitude of 4.1 kilometers. Combining these results leads to a final answer of 4.1 kilometers, 20 degrees east of north. The distance traveled is the last topic of this lecture. It is the length of the trajectory followed by an object during a given time interval. we will use the variable letter capital L for the distance traveled. If you cut the path into infinitely small, essentially straight sections, and add the lengths of these tiny sections, you would get the distance traveled. There are some similarities with displacement. First, you need to provide a particular time interval for both of their calculations. And secondly, they have the same measurement units like meter or kilometers. However, they are not the same thing. A displacement has a direction in space, and a distance traveled does not. There is a slight connection in the fact that if the trajectory was a one-way straight line, then the distance traveled would be equal to the magnitude of the displacement, provided that they are evaluated over the same time interval. Otherwise, the distance traveled is in general larger than the magnitude of the displacement. Let us look at two examples to illustrate the difference between displacement and distance traveled. The first one is a one-dimensional case based again on a trip along the straight road between Toronto and Montreal, which are 600 kilometers apart. The trip is a straightforward return trip, Toronto, Montreal, Toronto. The displacement is 0 because the initial and final positions are the same, the one defining the location of Toronto. However, the distance traveled is 1,200 kilometers, twice the distance between Toronto and Montreal, because the car has to travel that path twice. The second example is a similar but two-dimensional case. The object is traveling along a trajectory in the form of a circle. If the time interval is for one full rotation, then the object will return to its starting point, so the displacement is again 0. But the path traveled is the circumference of the circle given by this equation. Now that the displacement of an object has been defined, it is time to define another very important quantity, the average velocity. This will be the subject of the next installment.